algebra. Let us denote it by G, German G here, so which is GLN, which is also denoted by GLN, and it was the Lie algebra consisting of n by n matrices over C. Okay? And we have seen that it has triangular decomposition. So here n plus denotes the subalgebra of strictly upper triangular matrices, and H is the subalgebra of diagonal matrices. And well, consider a finite dimensional representation of G, which is GLN. And then it means we have a Lie algebra homomorphism from G, which is GLN, to general linear Lie algebra on V. And let us assume V is an m-dimensional vector space. Then it is just GLM. To emphasize, it is m by m matrices over C. Let us denote by GLM. Then an n by n matrix will be mapped onto what? How shall I write? I don't know. Maybe rho X, say KL. Here, this is m by n matrix. And we say rho is a polynomial representation of GLN. So here German G will always denote the n by n matrices GLN if the entries of rho is a polynomial in Xij's or KR. And then the representation of rho will be called a polynomial representation. And in my lectures until tomorrow, we will focus on polynomial representations of GLN. Okay. And let us recall the following. Recall the special generators of G. So E sub I was upper triangular matrix I plus 1, and Fi was lower triangular matrix I plus 1I. So here I runs from 1 to n minus 1, and we denote by K sub J the diagonal matrices where I runs from 1 to n. Then n plus is generated by E sub i's as a Lie algebra. And n minus is generated by Fi's. And the H is generated by KJ's, and well, since it is trivial Lie algebra, it is actually same as the vector space spanned by K sub J's. Now we will define linear functionals epsilon j's from H to C to be dual basis of Kj's. So epsilon j ki is defined by the Kronecker delta. Okay. And we will consider the free abelian group with the basis epsilon j's. Okay. And we consider the subset, so which is denoted by P plus in P if lambda I is a weakly decreasing non-negative integers. Okay. So P is usually called the P is usually called the weight lattice, and P plus is called the set of dominant integral weights. So let lambda be a dominant integral weight. Then we can write lambda as a sum of epsilon i's with weakly decreasing non-negative integers lambda i's. So it can be identified with the partition. So lambda 1, lambda 2, lambda n of, maybe we can denote by capital N, which is sum of lambda i's. Okay. And well, maybe I would like to remind you that the partition of positive integer is what? A sequence of non-negative integers, weakly increasing non-negative integers, whose sum is that positive integer. So for example, say maybe 7 is better. 7, then 3 plus 2 plus 1 plus 1, for example. Then 3, 2, 1, 1 is a partition of 7. And it can be identified with so-called Young diagram. So we put boxes in the first row. The number of boxes should be lambda 1. So we put lambda 1 many boxes in the first row. And we put lambda 2 many boxes in the second row, etc. And put lambda n many boxes in this last row. Then this is called the Young diagram, and or in combinatorics, Farrell's frame or Farrell's diagram. So in this case, for this partition, we can identify this as the Young diagram. Consists of 3 boxes, 2 boxes, and 1 box at each row. Okay. So what we have seen is that we can identify the set of dominant integral weights with the set of partitions. Okay. Now, yesterday,
what number?
it can vary.
Yeah, but
So,
yeah. So are you specifying this n or are you
No, it can vary.
every collection?
Right, right. Collection of every positive integers. So the set of all partitions of all positive integers. Now, yesterday, in the end of my lecture, we have seen that the representation of Lie algebra is the same as the representation of it's universal enveloping algebra. So, we consider a representation of a GLN, G module, is said to be a highest weight module, with the highest weight lambda in P if there is a non-zero vector V in V, a G module V, such that first the whole module is generated by this one vector. So V is a cyclic module. Okay. So it is generated by this vector, and you add to all the elements of G. So here U of G means the universal enveloping algebra of G. Second case, act on V as the linear functional lambda, and finally EIs should annihilate V. So for this, there are two extreme examples. Yes?
Does it work only for the G, the GLN, or?
It works for every cat-smooth algebra. So it especially works for GLN, yes. But for any reductively algebra too. And actually what I'm telling you, well, most of what I'm telling you works for general cat-smooth algebras as well. So there are two extreme examples. First, so for a weight lambda, let us note by J lambda be the left ideal of universal enveloping algebra of G, GLN, generated by the following elements. First, epsilon EIs and lambda H minus lambda H times 1 for H and H. So H means the diagonal matrices. So you can change it to KJs because they are the generators. And consider the quotient of U of G by J lambda. And let us denote it by M of lambda. Then by left multiplication of U of G, M of lambda becomes a G module or a UG module, and it is called the Boma module. Then, well, if we set V to be the coset of 1, okay, then we can easily see that it is annihilated by EIs because J lambda is generated by E sub i's too. And then H acts as lambda of h on V for any diagonal matrix, because that's how we took the quotient. So that's, and also, since one generates u of g, so m of lambda is generated by this single vector. So that is m of lambda is the highest weight G module with the highest weight lambda. Okay. What is important about m of lambda is that actually this is proportion every highest weight G module with highest weight lambda is a quotient of m of lambda. It's a homomorphic imagery of m of lambda. So in that sense, in this sense, m of lambda is a universal object in the category of highest weight modules. Okay.
What does this mean? I'm highest.
Highest weight. Good question.
It's very abstract.
Right. Why is it called highest weight? And this is the example, right? Suppose n is 2. Then we only have E1, F1, K1, K2. Okay. Suppose lambda is m times epsilon 1. So lambda K1 is m, lambda K2 is 0. Okay. Then have is exactly the same as what Professor Seo asked yesterday. For the consider the polynomial, the space of polynomials, Ct. So V is a polynomial in T. So this is the basis generated by 1, consistent of 1t t square cube. Then actually the polynomial representation that we had yesterday is the same as m times epsilon 1. And here the weight is lambda, and the other weights are actually less, in the sense that let alpha 1 be epsilon 1 minus epsilon 2. Then by applying f1s here, then weights are decreased by alpha 1s. Okay. So this is the highest weight. In this sense, it's the highest weight. The biggest, or it's highest. Okay.
Any alpha 1 you have, what could you say again, please?
Alpha 1
Yeah.
is just, this is definition. In general, we define alpha I to be epsilon I minus epsilon I plus 1. Okay. So if you apply F1,
What was F1? F1 was
so which
F1, yes.
it's a lower triangular matrix in this case. So if you apply, then what is the weight? When you apply K1 and K2 here, then it acts as lambda minus alpha 1. So at the first level, acts as a scalar of lambda minus alpha 1 times h. Of h, as this scalar. And next level, it works as lambda minus 2 alpha 1 in h, etc. So at each step, the multiple of alpha 1 is being subtracted. So in that sense, this is highest weight. Okay. And moreover, let R over lambda be the sum of all proper submeasures of M of lambda. Then any weight of R over lambda cannot be the same as lambda, because once it is same as lambda, then it contains a scalar multiple of V, then it will generate the whole module. Okay? And since we took the sum of all proper submodules, this is a maximal submodule and unique. Because it's sum of the all proper submodules. So we can take the quotient of M of lambda by R of lambda, and which we usually denote by V of lambda. Then by definition, it is necessarily irreducible module. And moreover, every irreducible module is obtained this way. So meaning that every finite dimensional polynomial representation, or G module, arises this way. So has the form V of lambda for a unique, actually dominant integral weight P plus lambda. That means finite dimensional polynomial representation of GLN are actually in one-to-one correspondence with the set of partitions with at most n parts. That's what usually combinatorics people calls. So I mean, we just have parts, number of parts is at most n. Okay? So one of the interesting problem would be how to construct an explicit basis of V lambda for each partition lambda.
So here n lambda is the one which you defined in the example 1?
That's right. So I erased it, but the maximal submodule, when the highest weight is m epsilon 1, is after t to the m plus 1. This part is the unique maximal submodule, which is some whole thing. Okay. And then the remaining thing is m plus 1 dimensional representation of GL2 or SL2. In this case, the same. Okay. But here, this is just only one partition, M. So that means number of M boxes in the first row only, in this case. Now, to construct an explicit basis of GLN module V of lambda, we will move to quantum version of GLN. Okay. So So next topic is the quantum algebra UQGLN. Here, Q is an indeterminate, and we will use the similar symbols for the generators. So we define the algebra UQGLN to be the associative algebra. The associative algebra over the field of rational functions in Q. So we put one more variable generated by the symbols E sub I, F sub I, where I runs from 1 to n. And we will use so-called group-like notation, Q to the kj, j runs from 1 to n.
It's a function from CQ or?
Yes.
Is it separate brace or singular brace?
This is the field of rational functions in Q.
Yes, but generally, some of the people were using actually infinite series and infinite series.
I would use formal power series this way. Okay. If you want, you can use Laurent polynomials, something like that. So CQ is a rational function field, or field of rational functions in Q. Okay. Now, so let me state the defining relations. See here, Q to the kj's are commutative. I don't know. Maybe ki plus kj. So here, ki is a diagonal matrices, and we will just use the symbols Q to the kj, which is parameterized by diagonal matrices. Okay? And EI and FJ almost commute each other. And here we have quantum version. Q minus Q inverse. And if you remember the commutation relation for the Lie algebra GLN, then you take the limit as Q approaches 1, then you will get Ki minus Ki plus 1. And usually physicists prove it using L'Hopital's rule. So since some people are very creative, and Q to the Ki and E sub j satisfy the following commutation relation: alpha j Ki and Ej Q to the Ki. Here, alpha j means the difference between epsilon j and epsilon j plus 1. And if recall that epsilon j is a dual basis of diagonal matrices kj's. And then Q to the Ki commuted with Fj as Q to the negative alpha j Ki and Fj Q to the Ki. And if Ij are far enough, then Fi, Fj, Fi commute. And same is true for Ei, Ej. if the difference is bigger than 1. Again, this should be regarded as quantum version of the defined relations for Lie algebra GLN. And when ij is 1, I mean if ij, the difference between I and j is 1, then we have the following defined relation: ei square ej minus q plus q inverse ei ej ei plus ej ei square is 0, and similarly for f's. Let me take half a minute break to take a shot. 이거 어디 갔어? 슬픈 일인데? 여기 꽂혀 있나? 그냥 할까요? 하나 더 주시죠. 여분이 없는 이유로 할 수 없이 녹음을 하지 못하는 좋은 핑계. 이런 어이없는 일이. 지혜야, 어이없다가 영어로 뭐냐? 요새는 어의라고 쓰는 사람들 정신 나간 거 아니야? 왜 어의가 나와? 그래서. Alright, so let me continue. I just gave you some time to digest the seemingly complicated defining relations. But when you put Q is 1, then we get the relations for GLN. In the case of Lie algebras, we took commutator bracket, but if you expand the bracket of xy to be xy minus yx as commutator, then you will get these same relations. Okay? So, with this definition, we can define the notion of high-straight modules. So here, let us note by uq plus to be the subalgebra generated by EI, and UQ.
When Q is 1, what is Q to the kj?
Is 1.
1?
Yes.
Then there's no generator for kj, or?
Actually, for that, Q to the kj, we took the generator Q to the kj minus 1 over Q minus 1. So, as Q approaches 1, it goes to kj. Yes. Actually, you need to be more rigorous in dealing with the Q minus 1 limit. Okay? But as I said, you factor right Q minus 1 and put Q is 1, then you get this. Well, I will get back to this issue a little bit later, then, if possible. All right, anyway, let me denote by UQ minus the subalgebra generated by FIs. And UQ0 to be the subalgebra generated by Q to the kj. Then we can prove that UQG is isomorphic to the tensor product of UQ minus UQ0 and UQ plus. So when Q is 1 for the Lie algebra GLN, this decomposition follows easily from Poincare-Berkowitz theorem. But for the quantum case, we need to prove it. Now,
summation, right? In the Lie algebra representation,
yes.
you have summation.
So yeah, that's right. For G, it has direct sum decomposition, but for its inverse enveloping algebra, then we have tensor product decomposition. Because consider ordered basis of n minus, h, and n plus. Then basis of u of g will consider monomials in this order, which coincide with the basis of this tensor product. That's Poincare-Berkowitz theorem. And we quantize its universal enveloping algebra, not the Lie algebra itself. So, we may define the notion of high-state modules for the quantum algebra UQGLN. So, say a UQG module V to the Q is called a high-state module with high-state lambda. And we mimic the definition of high-state module for GLN. So if there is non-zero vector in VQ, such that first VQ is generated by this single vector, and Q to the Kj acts as Q to the lambda of Kj for J from 1 to n. And finally, V must be annihilated by E sub i's. So while Kj acts as a scalar lambda of Kj, Q to the Kj acts as scalar Q to the lambda of Kj.
So this lambda is same as the previous one?
Yes, the same as previous one. Lambda belongs to the weight lattice, which is a free abelian group with the basis epsilon i's.
Epsilon I are same.
Yes, epsilon I is the same.
From the
Diagonal matrices to linear function on the set of diagonal matrices. Same thing. And then it is an exercise to define the notion of formal modules and irreducible high-state modules. Okay. You can define the formal module to be the quotient of UQG by the left ideal generated by E sub i's and Q to the Kj minus Q to the lambda Kj times 1. Okay? So just quantum, you exponentiate. Then, what do we mean by taking limit of Q approaches 1 of UQ of G is the same as U of G, and limit Q approaches 1 VQ lambda is V lambda. What do you mean by this? We need to be a little bit more careful. So let us denote by A sub 1 the localization of polynomial ring C of Q at the prime ideal Q minus 1. So what is this? This is the quotient of polynomials whose denominator does not vanish at 1, right? So localization by prime ideal. So yeah, okay. I mean I don't know. Then let us note by U sub A1G to be the subalgebra, A1 subalgebra of UQG generated by EI, FI, Q to the KJ, and additional element Q to the KJ minus 1 over Q minus 1. Okay. And if VQ lambda is generated by this highest weight vector, say V of lambda, then we will denote by V A1 lambda this U A1G module generated by this vector. Okay. So this is the definition. Then what we know is well, consider the quotient of maximal ideal generated by Q minus 1 here. Since we have localized it, it's a local ring with a unique maximal ideal, which is generated by Q minus 1. Okay. Then it is isomorphic to the complex field. So any element here, say what, F over G, would be mapped onto F1 over G1. In particular, Q will be mapped onto 1. Okay. So if we consider the extension of A1 form, so consider C and A1 form of UA1G. So here C was identified with the quotient field, and let us denote it by U1G. So by extending scalar means actually we took the limit Q approaches 1, limit of Q going to 1. Okay? Because by Hungerford, page 15, line 3, this should be the same as the quotient. Okay? Even though I spoke in English, maybe only Koreans would understand this joke. When I gave similar talk in Seokjin University, and I mentioned in other context, I mentioned page 50 and line number 3. And Professor Park Jung-hyung asked me, in that book, is it true that some materials on representation theory was written? Well, when you make a joke and the reply is serious, then and here again, V super 1 of lambda is taken to be the extension of the A1 lambda. Okay? So by this, well, when we say we take the limit of Q approaching to 1, we mean this. We take this tensor product, I mean extension of scalar. We identify complex field with this rigid field. Okay, then we still need to prove the following theorem, which is called the classical limit. Here, U sub 1G is actually isomorphic to the universal enveloping algebra of GLN. And V1 lambda is isomorphic to the highest weight module for GLN. Okay. That's the known theorem. In particular, when you would like to understand the dimension of V of lambda, then what is dimension of VQ lambda? Okay. Then since A1 is principal ideal domain and A1 lambda is a free module, etc., this must be same as rank of A1 module V1 lambda. Again by theorem 5.10 at chapter 4 in Hangul 4. Maybe some of you actually will go and open the book.
That's in chapter 5, section 3.3.
But I think
Page 325.
right. Probably this may be actually true. I didn't want to memorize it. But anyway, by that, this is the dimension of C of V1 lambda. Okay? So, if you want, the main purpose is to try to find the basis of V lambda. Then instead, we may find a basis for VQ lambda. Okay? I did not define the notion of characters, but if we try to understand the character of this function, this module, then we can, to the character of this module, then if it's sufficient to understand the character of this module, which is usually more complicated because you put Q, but it's not usually true. How can I say? This is not a good explanation, but you have a line, and here is point A, and here is point B. At Q is 1, you can never get to B, from A to B, because there is a line. But if you have quantum deformation, then you can go from A to B. Right? That's the basic idea of quantum mechanics. So. Anyway, so we will consider Q-deformed algebra and Q-deformed representation. So now, well, what I have said is to understand the situation at Q is 1, it suffices to understand the situation at generic Q. In particular, we will try to understand the situation at Q is 0. Okay? So, that's the motivation of crystal basis. So let V is an element of VQ lambda. Okay. And I want to put mu in the sense that this is the common eigenvectors for q to the j. SNU as q to the mu kj u for all j. Okay. So this is the definition for VQ lambda mu, which is usually called
Mu is a number or what is
mu is again an element in weight lattice. Okay. But here lambda is a partition or a Young diagram, but mu is an element in the weight lattice. Okay. And then by using the theory of SL2 modules, V can be written uniquely as follows. So V0 plus fix I, which is an element from 1 to n minus 1. And then every V can be written uniquely as follows. V0 Fi times V1, Fi square times V2, etc. and Fi n times Vn. Here, Fi to the k divided power means Fi to the k over k factorial with bracket. What do we mean by k factorial? So here, k means q to the k minus q to the negative k over q minus q inverse. Okay? Then when q approaches 1, in this case, we can really use factorization or L'Hopital's rule, and we get k, right? And vk's are annihilated by ei. For all k. So what I said is every v can be expressed as a sum of fi to the k times vk in a unique way where vk's are annihilated by e sub I. K runs from
K is an
integer
integer?
0 to n, 0 to n. Any non-negative integer. Then for each I, we may define so-called modified root vector operators or Cauchy operators as follows. We define ei tilde v to be k bigger than 1, fi to the k minus 1 vk, and fi tilde u to be k bigger than or equal to 0, fi to the k plus 1 v sub k. Okay.
What is this statement? V is V0 plus F from the, is this a fact or what?
It's fact. We need to prove it. We can express v as this sum, right? Uniquely. I mean, v0, v1 to vn are uniquely defined.
For fixed I.
For fixed I.
If somebody fixed I, then you can.
Right.
So you have n different expressions.
N minus 1 different. Yes. But it depends on v too. So for each v. So this way we define some linear operators ei tilde and fi tilde on v q lambda. Okay. Now we consider a limit at q0, meaning that we consider the localization of polynomial ring at q, at the prime ideal generated by q. Okay. Then we define the notion of crystal basis. A crystal basis of this irreducible highest vector module VQ lambda is a pair L and B, where first L is a free A0 lattice of VQ lambda. What does it mean? L is a free A0 submodule of this vector space VQ lambda. So free A0 module. And if we extend the scalar, then we can recover this. Second, B is a C basis of L mod QL. What does it mean?
VQ lambda is a A0 vector space, or?
VQ lambda is a CQ vector space, and A0 is a subring of CQ. So it's like when you consider Q and Z, so Z corresponds to A0, and Q corresponds to CQ.
Okay, so the A0 is
Integral form.
like an integral.
Right. Integral ring.
Integral lattice.
Right.
And a vector
Right.
space.
Right. So in this case, B is a C basis of L mod QL. What does it mean? So L mod QL is actually you extend the scalar of L to C. Then this is the same, right? C is what? You take the rigid field of A0 by the maximal ideal generated by Q. Okay? Then again by page 15, number 3, line number 3. So, in short, B, roughly speaking, B can be considered as a basis of L at Q0. Okay. And finally, actually there are